is here and also everybody who is trickling in. I think we're going to introduce our speaker. So we have, this is our second co-webinar with another CLF hub. We had one a couple months ago with CLF Rocky Mountain, phenomenal webinar on building reuse and policy surrounding that, and basically designing for deconstruction. And this webinar, we are co-hosting with CLF San Francisco. It's a bio-based building materials webinar, and we have 3 phenomenal speakers that are going to be presenting on their work. So we have Massey Burke, who is the executive director of the California Structural Building Association. She's the co-founder of Verdant Building Products, a biomaterial specialist for Verdant Structural Engineers, and a bio-based design build consultant in the San Francisco Bay Area. She began as a hands-on practitioner 2 decades ago and currently works on research, design, product development, and implementation of bio-based low-carbon building techniques. She helps clients and architects and contractors design for and manage construction with natural materials. And she partners with organizations including AROP, Stop Waste, and the Carbon Leadership Forum to generate technical information and help remove barriers to scaling up natural carbon sequestering building methods. And then we have Kate Chilton, and she's the Chief Sustainability Officer at BAMCorp. As the Chief Sustainability Officer, she engages with all aspects of the fast-growing climate-positive building products startup. Her primary focus is on leading the development of the company's sustainability assets and public sustainability voice, as well as finding new ways to increase the sustainability of BAMCorp's products and operations. She also serves as the company's dedicated LCA practitioner, leading the effort to publish BAMCorp's first ever EPD, which is so cool, and driving efforts to modernize carbon accounting standards throughout the industry. And Katie Poss is the Director of Global Policy and Procurement at Building Transparency, who were the developers of the EC3 tool and Tally LCA, which so many of us use. If we don't use Tally LCA, I think probably the 90% of us on this call have used EC3 at least at one point. In this role, Katie supports the nonprofit's core mission of providing the open access data and tools necessary to enable broad and swift action across the building industry in addressing its role in climate change. Prior to joining Building Transparency, Katie served as Director of Sustainability Initiatives at the National Ready Mix Concrete Association. So she knows what she's talking about, and as a Sustainability Program Manager at Turner Construction for its data center portfolio. She is a board member of the California Structural Building Association, which also known as CASBA, and serves on New York State's Embodied Carbon Technical Advisory Group. And with that, I will hand it off to our speakers.
Thank you, Rochelle, and thank you, CLF-LA and Bay Area, for having us. I'm very excited to be here to talk about this exciting topic. This family of materials is gaining a lot of attention. I think it's long overdue, and there's a lot of excitement around how we can use these materials in the built environment. So today we're just going to start with a little bit of level setting around some of this terminology. Thank you, Kate. So what does this term bio-based mean? So bio-based refers to products or materials made from renewable biological resources, such as those derived from plants, animals, marine or forestry materials. And according to the USDA, the term bio-based applies to materials whose primary content is derived from biological sources rather than fossil resources. The image on the right here is the cover of a report that Building Green recently published called The Promise of Bio-Based Materials and How to Use Them. Shout out to Brent Ehrlich and the entire team at Building Green. This is an excellent resource. It dives deeper into what bio-based means. It talks about a lot of the things we're going to talk about today, how hemp and straw and bamboo are being used in the built environment. What are some of the challenges with these materials scaling? So if you're interested in learning more after this webinar, I would strongly recommend that you check out this report. Next slide. So if you all are familiar with LCAs, and those of you who have looked at EPDs before, you may have come across these terms GWP biogenic or GWP bio in some cases, and GWP fossil. So I want to explain the difference between biogenic and non-biogenic carbon. So GWP fossil refers to the global warming potential from greenhouse gases that are derived from fossil carbon sources. So think about, things like coal and oil and natural gas. This source of carbon has been stored underground for millions of years in the form of fossil fuels. And when these fuels are burned for energy, the carbon that was locked away for millions of years is released into the atmosphere as carbon dioxide and sometimes other greenhouse gases. So these fossil carbon emissions are contributing directly to the increase of atmospheric CO2 levels because this carbon was not previously in the active carbon cycle. So ultimately, this leads to a net increase in global warming potential. So GWP biogenic refers to the global warming potential. And just another note on terminology, when I say GWP or global warming potential, it's essentially synonymous with embodied carbon. But GWP biogenic refers to carbon that is derived from those biological or bio-based materials. Again, plants, animals, things like organic waste also fall under that category. And biogenic carbon comes from sources that are part of the natural carbon cycle. So as we all know, plants absorb carbon from the atmosphere, carbon dioxide from the atmosphere as they grow during photosynthesis. And when these plants or other organic materials decompose or they're burned in some cases, that stored carbon is released back into the atmosphere. So that release of biogenic carbon, it doesn't typically contribute to a net increase in atmospheric CO2 because it is already part of that short-term carbon cycle. But the timing and management of those biogenic emissions really matter. And Kate's going to get into that a little bit more detail here in a moment. But so, if these forests or other carbon absorbing ecosystems are not replenished and they're not managed well, then these biogenic emissions could still contribute to global warming. So just to summarize that, GWP fossil is from long stored fossil fuels. GWP biogenic is from recent biological materials in the active carbon cycle. GWP fossil typically results in a net addition of CO2 to the atmosphere, and GWP biogenic is typically neutral over time unless it's managed poorly. Kate, I'll hand it off to you.
Katie. So a little bit more vocabulary defining, and for those of you that don't know, but I think everyone here does, what is an LCA? It is essentially a quantitative and objective way of measuring the impact that a product or a material or a building has on the environment. And so there's a bunch of different environmental impact categories that are produced from an LCA. But for the purposes of the next few slides that I'll cover, I'm going to only focus on carbon. But as you can see, this chart does a really good job of showing what do we actually include when we say embodied carbon and what do we include when we say operational carbon. Most people in their minds think of this product stage only, and that is where the majority of embodied carbon is created or produced, or emissions, I should say, are produced. But there is embodied carbon impacts throughout the life cycle of a building. And then you see on the bottom, operating carbon is really just associated with the use of that building. But when we think about LCAs and assessing carbon, and specifically biogenic carbon, there's really two main approaches today in current carbon accounting standards that are what we call static. And so there's the 0-0 approach, which essentially ignores biogenic carbon altogether. It doesn't account for it. And there's the -1+1 approach, which is probably the most common way, which assumes that there is biogenic uptake in the forest system or the plantation or wherever the material is harvested. It flows through the different systems, and then there's an equal amount that is released at the end of the life cycle. And what's important to note is both of these are carbon neutral. So when you look at the totality, there really is no impact of that biogenic carbon. And increasingly, one of the big criticisms of these approaches is that they don't account for timing of emissions. And so by not accounting for when the carbon is being released, when it is being taken up, you're not accounting for the rotation period of biogenic materials. You're not accounting for the speed of regrowth. And that really is one of the key differentiators between different bio-based materials, is how fast they regrow. And so in order to account for this, dynamic LCA approaches are becoming much more common. And really their objective is to consider this timing component of biogenic carbon. And there's really two ways to do this. There's the backward-looking approach, which assumes that there's biomass that grows in the system before you harvest it. That's where the uptake is happening. And there's the forward-looking approach, which assumes you harvest and then an equal amount is replaced and then regrows. And so when we think about wanting to account for speed of regrowth, the forward-looking approach, generally speaking, is more commonly used because that really gets into the rotation period component of this problem and being able to assess the differences between short rotation materials and long rotation materials. The last thing I'll say before handing it off is related to the metrics that we use to assess materials. So Katie just gave a brief definition of GWP, global warming potential. That is the metric that LCAs output specifically for the carbon component. There's, as I said, lots of other impact categories. But increasingly global temperature change is being used to assess these materials because you're able to use that in comparison to targets that are being set. So when you think about the Paris Agreement, those targets are set in terms of Celsius that we want to prevent warming. And so having a temperature change versus just an amount of heat that's being trapped is a little bit better in terms of measuring the impacts of these products. And when you take a dynamic view, as this graph does, you're really able to see the impacts of different materials based on that speed of regrowth. And so here you see a number of different biogenic materials that are placed on this plot. The uptick happens because of emissions that are produced, again, in that product stage. But then the downward slope is directly correlated with how fast these materials grow. And so the straw has this little tiny uptick, but then it immediately becomes negative on the graph because it's storing more carbon than it's releasing, and it's immediately recapturing that carbon. And so you're able to see here that the fast growing materials are able to achieve this net cooling impact much sooner than materials that have longer rotation periods. And that's really key when we think about assessing materials in terms of their climate mitigation potential.
All right, yeah, just speaking to this slide, we spend a lot of time talking about bio-based materials and carbon specifically, and that's a lot of what gets people interested in bio-based materials. But there are many other benefits that I think people are aware of. And one thing that's bothered me for a long time, I started working with what used to be called natural material. I mean, they're still called natural materials, but what was called the natural materials movement, which is basically grown into, and I guess you could say merged with, the bio-based materials movement or area of interest. But I've worked with natural materials in building for 20 years, you know, when it was very grassroots, and then has grown into many other parts of the built environment, no pun intended. And what always bothered me about it is that it was very difficult to make the case. You know, it's a funny time for me right now because natural materials people have been niche and kind of sidelined for so long that it's very strange to be suddenly front and center. And so we're kind of trying to catch up in some ways. But anyway, where I'm going with this is that I'm used to trying to explain to people the benefits of these materials. And until very recently, you had to make one-on-one cases for a natural material. And if you're trying to compare it, and in that modality, by which I mean, you know, just expense, or just, you know, carbon, or just, you know, biodegradability or toxins or whatever, it's if you compare natural and bio-based materials one-on-one to other building solutions, they're not always, you know, cheaper or quicker, or, you know, the sort of offer the traditional benefits that people ask of industrial building materials. But I was having a conversation with one of my favorite policy people 2 or 3 years ago, and she said, "Oh my goodness, if I think about all the buckets that I always hear about in policy, which are, there's a lot of them, but these are the 5 big ones that you often run across. So healthy buildings, healthy for humans and ecosystems, climate and carbon, circular economy, social equity, and increasingly bioregional resilience, especially post-pandemic. A lot of sort of conventional or industrial materials may address 1 or 2 of these, but the only thing that addresses all of them is bio-based materials. And that so delighted me that I started using this Venn to talk about natural and bio-based materials, because it was the only tool I had come across that really expressed, what I feel is is this holistic benefit that you get from working with these that's really hard to express in conventional metrics, by any conventional metrics. And what's really fun for me is that I actually used this on my board call for CASBA a couple days ago, and my David Arkin, who's used to be the director of CASBA and is still on the board, said, "Where'd you get that?" And I said, "Oh, it came out of a conversation a couple years ago." And he said, "Well, just so you know, the AIA Materials Pledge and the Mindful Materials group are using something really similar." And so I think we're at a moment where thinking like this is becoming emergent and really, I wouldn't say it's mainstream yet, but it's mainstreaming. All right, handing it back to y'all for the next slide.
So we're going to talk about 3 different fast-growing fibers today. And I wanted to hit this point home again in terms of fast regrowth and why does it matter? And really there's 2 reasons that kind of go hand in hand. The first of which is this concept called the time value of carbon. It's very similar to time value of carbon or time value of money in finance, but it essentially is this idea that carbon that is sequestered or emitted today is more valuable than that which happens in the future. And one of the main reasons for this is the presence of tipping points in our climate system. And so because of these tipping points, which if crossed, are going to have invariable, irreversible, and virtually catastrophic effects on our system, we don't really know the full impact of what will happen. We need to be doing everything that we can in order to avoid these. And so because of that, it means that much more importance is being placed on what's happening in the near term versus what happens in the long term. And so that's one of the reasons why fast regrowth matters, is because we're able to do a lot more in a short period of time. And so the first fiber that we'll talk about is bamboo. It's extremely fast growing. It can reach full harvest maturity in 5 to 7 years. And because bamboo is a grass, not a tree, which is a common misconception, it's able to be harvested differently than trees are. And so you're able to kind of selectively harvest roughly 20% of it each year after it reaches maturity. And then once it's mature and you cut down a culm, it'll immediately regrow that culm in the next growing cycle. And so it's almost an annually renewing crop once it reaches that harvest maturity in 5 to 7 years. So extremely fast growth. It has lots of other ecosystem benefits because of this harvesting technique or methodology. So because you're not clear cutting like you do with trees, you're able to minimize the amount that the soil is disrupted, and you're able to increase biodiversity because you're really keeping that ecosystem intact for the most part. And then lastly, it can be a powerful restoration tool. It can grow on degraded lands. It can help with soil erosion. So there's lots of reasons, both from a soil restoration as well as a carbon sequestration perspective, to establish new bamboo plantations. And so really to hit home the 2 key benefits of bamboo, the first is land use efficiency. So we're currently facing a global land use squeeze. And so using fibers that are much more productive with less land is really going to be critical. And so because bamboo is very efficient in how much fiber it's able to produce, you're able to use less land. And then again, that greater carbon sequestration capacity that really comes from this perpetual annual harvesting. So a single column of bamboo does not hold more carbon than a tree trunk. But if you're able to harvest every single year, year after year, over time, you're actually going to see much greater carbon removal capacity for bamboo. And so when we think about building materials in the built environment, there's kind of two main ways that bamboo is used. The first is known as whole pole construction. It's very common in the global south, in South America, and in Asia. And what's emerging now is engineered bamboo. And so that's where Bamcor falls. But that's becoming more prominent in the global north, in Europe, North America. The logos on the bottom of the slide are by no means an exhaustive list, but just to kind of give you a sense of who the different players are in each of these spaces. And so, as I said, Bamcor, we are in the engineered bamboo category. Our in-market product is a custom prefabricated structural framing system. And so we build what we call prime wall panels out of bamboo. We also use eucalyptus and wood, and create these really, really strong panels that serve as the frame of the building. And so they're prefabricated, which means that they come to the job site with everything pre-cut, the walls, the outlets, the doors. And so that has the benefit of both speeding construction on site as well as reducing on-site waste. And so really you can think about the benefits of this system by having all of the complexity associated with framing on site gets taken out and it's getting put into our factory. Another benefit of the prime wall is the fact that we're having this panelized system, which removes, virtually all studs, creates a very thermally efficient building envelope. And so because it's thermally efficient, it's energy efficient, which means it reduces operating emissions. And because it's bio-based and because it uses fast-growing fibers, it has a really great embodied carbon story. So we're proud that we kind of hit both the operating and the embodied carbon components. And then there's lots of other attributes about having a panelized system over traditional stick framing, including higher acoustic opacity. So our buildings are much quieter and more comfortable to occupy. And again, they're really fast to build. You don't need a lot of machinery or really skilled labor, which is one of the key benefits from a construction standpoint. It's one of the main pain points that we hit, and why builders like working with us is because it's a really simple and easy system to install. So now I'll hand it over to Katie to talk about hemp.
Yep. So I'm going to talk a little bit about how industrial hemp is being used in building materials. I have a little bit of hands-on experience working with hempcrete. I also used to volunteer with the U.S. Hemp Building Association, helped them set up their regional leaders program, and received a grant to research it in college. So just really fascinated by all the ways that industrial hemp can be used in building materials and other industries. There's a couple of examples here on the screen. On the far left, you see hemp flooring manufactured by a company called Hempwood. Their factory is actually about 20 minutes away from me here in Western Kentucky. They also have a factory in Europe, I believe in Belgium. The oil from the hemp plant has been used in wood finish and deck sealers. There's a hemp fiber bat insulation. You might have heard of hemp wool made by Hempitecture. It's also manufactured in Canada and I believe in Europe as well. That's made from the hemp fibers, basically a replacement for fiberglass bat insulation. And then hempcrete, you've probably heard of, sometimes called hemp lime, is basically a cast in place infill insulation. So thank you. Great progression into the next slide. What is hempcrete or hemp lime? I'm using the term hemp lime, and actually the USHBA had an entire initiative around the terminology because hempcrete is a bit of a misnomer. Some people think that it's a replacement for ready-mix concrete. It's not. It's not nearly as strong as ready-mix concrete. So that's why the term hemp lime is becoming much more popular. But hemp lime is made from a combination of hemp shiv, which is the inner woody core of the industrial hemp fiber stalk, typically a lime-based binder. Sometimes natural cements are used, and water, and that's it. And it creates the end product that you see there on the right. Next slide. So as I mentioned, this term hemp heard also sometimes called hemp shiv, is that inner woody core of the hemp stalk. On the left there, you see industrial hemp fiber that's being harvested. Hemp fiber is an incredibly strong fiber, and it takes some specialized equipment called a decorticator to separate the fiber from the inner part of the stalk. So oftentimes, hemp fiber is grown for the purpose of using the fiber in things like textiles, and the shiv or the hurd is a leftover waste product of that process. On the right is a picture from Hempitecture's Innovation Lab, and it shows various samples of building grade hurd. There's a product that is very common. There's a contractor called Americhamp that pretty much exclusively uses Cannabat. It's a product out of France, and they actually have codes and standards that define building grade hemp hurd for use in building applications. It's my understanding there are some ASTM committees working on similar standards right now. Next. Just a quick note on binders. Sometimes you'll see hydraulic lime being used, something like natural hydraulic lime, NHL5 is an example. I don't know of any manufacturing here in the US. It's more commonly imported, though I might be mistaken on that. What I have used in my experience is typically a combination of type S hydrated lime and some kind of pozzolan. So we have used actually ground glass pozzolan on previous projects. I believe you could probably use fly ash, slag, some of those materials that if you're familiar with ready mix concrete, they're used in those applications as well to reduce the cement content. There are a number of pre-blended binders that are emerging specific to the use of hemp lime or hempcrete. And then there are also some natural cement binders. What you don't see on the screen here is Portland cement. It's been tested before. What happens is it basically chokes or creates an environment where the hemp lime cannot breathe. So for those of you who are architects or designers, hemp lime is a breathable vapor open wall system. And the Portland cement is not a good application or combination with the bio-based hemp fibers and hemp hurd. Next slide. There are various installation methods. The most common historically is to install formwork on either side of your framing and to basically pour in the hemp lime and tamp it and move your formwork up. It is a very labor-intensive process. So there have been companies exploring alternative installation methods to reduce the on-site labor time. Things like precast blocks or bricks, which you can see on the top right there, which are typically installed in the same way as a traditional masonry brick with a lime-based mortar. There are some companies experimenting with precast, prefabricated panels that are dried and cured off-site, brought on-site, and just installed just like other precast panels. And then on the bottom right, there's this system that, again, that company Americhamp is pretty much using exclusively. It is a spray applied system called the E-Reezy system that was developed in France and is made specifically for spray applied application of hempcrete or hemp lime. Next. And then I just wanted to end with some eye candy, just some examples of how hemp lime has been used. I think a lot of people often think that it's really only suitable for single family residential homes. That's not the case. It has been used in commercial applications, multifamily residential. I've just heard recently about a large multifamily residential project that's being constructed in the Northeast US, which is very exciting. And I think with that, I'll hand it off to Massey to talk about straw.
All right. I'm going to kind of sprint
Wait,
through
sorry,
straw just so we,
Massey.
yeah,
Could we, there's like one question in the chat, maybe we could
Yeah, go ahead.
get to it and then so somebody asked, how do we discount future carbon if we don't know time of the tipping point? That might be for Kate, I think.
So discounting carbon flows is another way to account for time. There's also an alternative metric called GWP bio, not to be confused with GWP biogenic. So there's lots of different methods for how to account for timing. Discounting carbon flows, I'd say, is the one that academics are the most, I'd say, skeptical about. because the choice of the discount rate is highly subjective. So I'd say it's not common. And we also, to the question, don't know when tipping points are going to be passed. So there isn't really a good method for choosing a point in time and then discounting back from that. I'd say becoming more common is this dynamic LCA approach that looks at what the impacts every single year at any point in time are into the future. And that's tends to be a better decision-making tool than discounting carbon flows.
Okay, cool, thanks. And that eye candy was very cool, Katie. Thank you. All right, sorry, Massey, go ahead.
Oh, no worries. All right, I'm gonna sprint through straw, just so we don't run over. Go back one slide though, hold on. I'm the director of the California Straw Building Association, which is a nonprofit that has been around for 25 years and has its roots in what I mentioned before, what used to be just a grassroots natural building movement, or that's what we call it here and something like that in Europe, where the only people doing this stuff were owner builders and initially doing it illegally because there was no code. So this nonprofit was founded to basically try to remove barriers to straw construction and has been a community node for really since its inception 25 years ago with these crazy straw heads that got together on the Carrizo plain with a trebuchet and like, I mean, you know, so, and we're in this, as I mentioned, we're in an interesting moment of really scrambling to grow into our next role, as well as understanding what that is. So I mentioned all of that just to say, because I'm going to do a very fast overview, just know that CASBA is a California resource, nonprofit, open source content, has wrote all the code for straw, bale, and light straw clay construction, works on other technical issues around scaling straw, and now is participating and is one of the funders for the PCR process for biogenic materials that we'll talk about a little later in the presentation. Okay, next slide, please. What is straw? So straw is generally considered the byproduct of grain growing. And looks like some of the labels got left off this slide, but in the sketch there, the top of the straw plant is the grain, which is what we usually grow it for. And of course, the bottom is the roots, and the middle bit is straw. It's the stalk of the grain plant that's left over after the grain is harvested off the top. And the reason that you can build with it and why it isn't a rotting issue, why you don't have decomposition issues with straw unless it gets really, really wet, is because all of the nutrient value goes into the grain, and straw is really just silicon and carbon. All right, next slide. Interesting thing about straw, there's not really much processing that goes into it for what are currently the most typical types of straw construction. You basically just cut it down, bale it, and take it to the building site, or maybe do one or two other things. And so one of the very interesting things about straw that's kind of one of its superpowers is that its supply chain is very short and very transparent. Next slide. So you probably have heard of straw bale construction, which is the type of construction that the California Straw Building Association was originally organized around, and is literally taking bales of straw and stacking them up. Originally, people were interested in this because you can do a load-bearing straw bale wall, even in seismic zones where you stack the bales and then you frame a roof directly on the bales as the load-bearing element. But these days, typically straw is put in a framed system just because you get a lot more flexibility around door and window placement and structure and all sorts of other things. California, you can go, I think the prescriptive code is one story, but you can go up higher than that with engineering. And on the right here, you can see a couple. So the bottom picture, there's my eye candy for you. I actually, one of the things I still do is consult on finishes. And so you're looking at a clay plastered interior straw bale with an exterior of, I think it's actually siding with a lime plaster over it. So the exterior is a little bit conventional. This is a fire rebuild for a big common space down at one of our regenerative farms near the Bay Area. And then the floor is an earthen floor that I helped direct. And on the right, you can see, anyway, yeah, just people modifying bales on site. And so bale construction is definitely a very site-built process. Okay, next slide. You might, oh, looks like letters got left out of that too. That should say light straw clay. This is the other really common site-built straw system that people may be less familiar with because we don't use it as much in California. Not sure why. It's more common in Oregon. But it's a formed straw system. So it's a little bit like hempcrete, where you mix straw with clay and you form the walls. And you do need framing for this. Again, it's a bit labor intensive as with bale construction. But it's has a longer traditional history than bales, because bales only came into existence when balers came into existence, which I think was around the beginning of the 20th century. But light straw clay, obviously you can do with just straw. And variants of this can be found in the old timber frames of Europe that are several hundred years old. And then on the right here, the lower picture is actually my house, the one I'm sitting in. And it is a light straw clay remodel of a very funky stucco stick frame in the Bay Area. And so this is, I think, an underemployed form of light straw clay as an addition to existing buildings. And there are design considerations with that around vapor permeability and what surfaces you're going up against. But it's much more versatile just because you can control the wall thickness than bale construction. And then the upper picture of these two, we do a little bit of partnering with workforce development. Like I'm exploring how CASBA can help scale sort of labor skills that way. And these two ladies were a part of one of these programs. Having a great time with a very clay mix of light straw clay. All right, next slide. And then there's this really interesting middle ground. So straw bale and light straw clay are the two most common sort of grassroots, but also just now custom site-built forms of straw construction. And then several years ago, like this whole range of panelization began to emerge, and some of it is literally just bales panelized on site and then tipped up all the way to a panel product, which I am actually on part of the development team for. And so that's the image on the graphic on the left is the Verdant panel, which is a fully product form of a panelized straw wall system. And then the image on the right is the new Frameworks Griffin panel. I think they're calling it something else now, but it's a little bit less, the straw is less modified than our system, but it's still a product that you would receive on site rather than construct on site. And so this where the grassroots straw building world is kind of creeping its way out into products and different applications. And this is kind of this is the growing edge right now, is panelized straw. Next slide. And then there are a bunch of products. Some are old and got reinvented. Some are newer. Verdant panel, as I mentioned, were on there, the Griffin panel. Croft is another panelized product in Maine. A lot of what's interesting about the panelized wall systems is that they're still kind of thick, and so some of us are working to get that down to normal wall thickness and still get high R value, because if straw is unprocessed, the matrix is relatively coarse, and so you do actually need the thick walls for, you don't need a whole bale's thickness, but you need thicker walls to achieve at least California energy performance requirements. Straw block is a sort of a localized product in Oregon. Strategy is a straw filled wall system in Utah. Savic is another panel in Canada, insulating panel. Next slide. Then a bunch of European products, of course, some of which you can get here. People probably know EcoCocone if you know a panelized wall system, because they've been around a while and they've had a few projects in the US, not a whole lot. Mod Cells UK. I know of these others. I don't have a lot of personal experience with them, but just again, variations on insulating straw insulated wall systems. Next slide. And then not necessarily for insulation, but just boards. So compressed straw boards of various types from all sorts of places, but you may run across these or be able to find them if you're looking to source like a straw based product. Okay, next slide. Yeah, and then a little bit more on straw and carbon storage. This is a graph that we were so delighted, because what really began to change the conversation for straw as a relevant material, and of course all bio-based materials, is its ability to store carbon. And very quickly, the way that works is that the job of a plant, and especially a quickly regrowable plant, is to take atmospheric carbon and turn it into plant material. And so all of that atmospheric carbon stays put until the straw or the hemp or whatever it is decomposes. And typically that happens within a year, but if you put it in a building, it doesn't until you take the building down. And so that conversation and then the realization around embodied carbon versus operational carbon, as I'm sure this entire group knows, was really the game changer and helped people realize that these materials are relevant and a you know, superpower. But I think we're still coming to understand how to describe all those flows, and we're going to talk about the whole LCA and PCR process after this, because it depends on, you know, how do you know, where do you credit the carbon storage and, you know, the length of the carbon storage and all those issues. So this graph was made by the Department of Energy, I believe. And everybody was so tickled when it came out because we didn't realize that they were aware of these comparisons, and it doesn't get all of the bio-based materials. And it probably weights straw actually too much. The straw is all the way down there at the bottom, but it does capture the fact that there are very few emissions associated with straw production, and the volume of carbon that gets stored in a straw wall is quite high. And so when you look at it just in those simple ways, the net carbon storage of straw is a lot. But you know, a purely hemp-based material without the binder, hempcrete is less carbon storing, and I think laminated bamboo as well, just because of the other ingredients in the mix. But any plant-based material by volume is going to be extremely carbon storing. Okay, next slide. Quick note on scaling up. As I mentioned, you know, we've been grassroots for a long time and are exploring just other building typologies that, you know, certainly straw bales don't typically go into, and then straw has not yet gone into a whole lot. On the right is a multi-use building in Oregon designed by architects. I believe it's 3 stories, but that is a straw bale building that's framed and just clad on the outside with metal and wood, plastered on the inside. And on the left is actually, we asked and tried to answer the question, could you make a net carbon storing building and meet East Bay seismic codes with a multi-use building? And so that's a building model that came out of trying to answer that question. That was some work that CASBA did with Arup and some other consulting partners. And if you're interested, I can actually find the link to that. The building wasn't built, but we wanted to model enough of a building to make it tangible to people who might want to try to build something like this. And so I can drop the link to that report in the chat in a minute. Next slide. And then a really quick note on something that I'm kind of obsessed with, which is the relationship between using straw as a building material and land management. Several years ago, I did some work with some pioneers in regenerative farming in California who were really interested in soil carbon. And that was the first I had heard of thinking about soil carbon as a response to climate change, among other things. And also, as I mentioned earlier, one of the superpowers of straw is that you have these really short, very transparent, very accessible supply chains. And so you have an enormous opportunity to basically intervene in the entire system that produces straw, not just the product that you make. And the upshot is that land management matters. We're still trying to understand how much. If you know about soil carbon, that whole conversation, it's much more debated, I would say, than even just how we quantify carbon storage in biogenic materials in a wall, because it's complicated. But just to give you one example, this graph is from a farmer named Gabe Brown, who has been practicing carbon farming in North Dakota, I think, somewhere up there, for a long time. As you can see, this graph begins in 93. And what this graph represents is just adding all of the techniques that are known to help restore soils for multiple purposes. And actually, if you talk to farmers, they say that increased soil carbon is just a byproduct, because that gets you other things that you need for agricultural stability. And so not tilling is one thing, and then you add crop diversity, cover crops. I won't spend a lot of time on this, but if you want me to binge your ear about it some other time, I will. But the dotted line in the graph is the growth of the carbon stored in his soil as he adds these techniques. And so really the point here is that, yeah, land management matters. How much? Hard to say. It's complex, depends on what you're growing, depends on where you grow it, depends on the rainfall you get, like all sorts of stuff that affect soils. But it's really interesting area of biogenic building materials. And then on the right, California is just trying to do straw supply chain mapping as a part of really trying to understand and get more granular about how to participate in the land management component of straw. Okay, next slide. That might be my last one. Is that the last straw slide? Yeah. Back to you guys.
So I'll blow through these really quickly because I know that we are running low on time. But we just wanted to call out a couple other, fast-growing, emerging bio-based fibers that are being used increasingly in buildings. And so the first is mycelium. It's most commonly used, I think, as an insulation product. And so you can see a few of the producers that are been coming, as most things. I think it's started and has been more prominent in Europe, but is really starting to come stateside. And then the other is grass. And so this is also commonly used as an insulation product, but we're now starting to see with planted it being used in new applications such as a replacement for OSB that can be accompanied with stick framing, which is also a bio-based solution, but we'll stick to the fast-growing ones here. Okay, Katie.
Just a quick note on scaling bio-based materials, and let's talk a little bit about PCRs and EPDs. As I'm sure many of you are aware, there's a lot of interest right now in calculating embodied carbon and in the procurement of low carbon products at the federal level here in the US. Various states have buy clean policies. Also, private developers are establishing policies and requiring EPDs in their specs. And EPDs are the most common way to prove and validate the embodied carbon of a product. And it was a few years ago, I was talking to Dr. Will Srubar from CU Boulder, and I asked him, Will, why aren't there more EPDs for hemp and straw materials? And he said, because there's no PCR. So fast forward a few years later, we have just engaged Smart EPD as the program operator to develop a PCR or product category rule for this family of materials that we're talking about today. PCR and in combination with LCAs, these are essentially the backbone behind an EPD. And the PCR outlines the rules or guidelines that LCA practitioners follow to conduct the LCA, which the results of which ultimately end up in an EPD. Next slide. So CASBA is sponsoring the development of the PCR. We're engaged with Smart EPD, like I said, as our program operator who will ultimately publish it when the process is complete. And there are representatives from all of these organizations and more participating on the committee. Next slide. Just quickly, some of the topical areas that we are exploring as we progress through PCR development. We're still relatively early, but really starting to get into some of the nitty-gritty and looking at impacts of agricultural practices and trying to identify relevant data sets. I won't read all of these here on the screen, but just know that we are very much in the weeds, no pun intended, and really excited to start evaluating what data is out there and what gaps there are so we can be honest and transparent about the impacts of actually growing these materials and make sure that we are communicating those impacts as accurately as possible in EPDs. Next slide. Massey, I think you're going to touch on this one. Or do you want me to? Oh, you're muted.
Sorry, there we go. Yeah, I don't know that there's much more to say about this other than that it expands upon my point about land management and other benefits and or considerations around biogenic materials. These are a lot of these impact indicators are, in conventional EPDs are negatives, like you have to, how little acidification are you generating or eutrophication, and there are many instances through land management of biogenic materials or bio-based materials where you can actually increase biodiversity. You can actually reduce eutrophication. And so we're running into some other pretty interesting questions that are outside of typical sort of EPD format that we need to answer with this PCR and the EPDs for bio-based materials. Yeah, and then just a note on this, the Biden-Harris administration put out a whole lot of money as a part of the Inflation Reduction Act for EPD development. And the Hemp Building Institute was awarded $6 million to work on EPDs for all sorts of biogenic building materials, and create an EPD generator tool, which is something that's becoming increasingly common for groups of materials, to just help specific bio-based products rather than sort of general materials create EPDs relatively rapidly. And so that's pretty exciting. So that work is just beginning. Next slide.
Yep, and I'll speak to BAMCOR's. So we also got a grant as a part of the EPA grant program, and ours is focused on working with the ACLCA's open PCR standard. So they have a process to create addenda to the open PCR or to the PCR open standard. And we got funding to create the biogenic carbon addendum with the hopes of including some sort of guidance around how to dynamically calculate biogenic carbon in LCAs and EPDs. And so from a high level, the process will be forming a working group with both stakeholders from different industry players as well as academia, doing a set of research and analyses on existing approaches, dynamic approaches, figuring out what works, actually testing those on EPDs like BAMCOR's to see what the impact would be, then writing the actual addendum document, and then we'll go through the ACLCA's formal review and approval process, which does include a public comment period. And then lastly, quickly, just wanted to kind of throw out there that there are lots of developments happening from a public policy perspective. I think, Katie touched on a few of them earlier, but across California, there's the Buy Clean California, which is procurement based. There's Cal Green, which is, the building standards. In France and in Canada, they also have similar kind of green building standards, and all of these are focused on either mandating the assessment and reporting of embodied carbon, or directly calling out the procurement of sustainable and low carbon building materials. This is, again, not an exhaustive list, but just wanted to show that there is increasingly momentum around public policy in this space.
Massey, I think this is both of us. I'll just start by quickly saying, for those of you who are attending Greenbuild in Philly in a couple of weeks, there is going to be a carbon storing materials pavilion that's going to be highlighting a lot of companies who are using these materials that we've talked about today. And also Building Transparency will have a booth, and our booth wall panels are made out of hempcrete. So if you've never seen it in real life and want to come check it out, please come visit us at Greenbuild.
Yeah, and then just speaking more to how you might be engaged in helping scale bio-based materials. First of all, CASBA will be offering its annual conference next year, and we hop it around California. Last year it was in the South, and this next year it'll be in the Bay Area in early April, and we have a lot of fun. And it's also it's a really interesting bunch of people because we still have our old school grassroots people, and we've grown our participation and audience into a lot of people on this call and just a lot of other audiences. And so it's just last year someone said, I just love how many different types of people straw brings together. And I think that's a good description of the conference. And I also love that it's open source. So we're very, there's an ethic that goes with it that is helping to scale products that are obviously not entirely open source, but the community itself remains very open source and collaborative. So keep an eye out for that and do come if you can. It's a lot of fun. And then also find your local bio-based materials startup. There are so many, and they all need different kinds of help. Everybody's fundraising pretty much, looking for investors. The nonprofits that hold down the technical information are, of course, always looking for funders and donors, volunteers, and just all sorts of other kinds of help, graphic design, things like that. And so the cool thing is that there's a million ways to get involved in helping to scale bio-based materials, a bunch of different materials. So find one of the avenues that really takes advantage of what you want to do and what your skill set is, if you want to help scale. And then lots of other organizations that to be aware of, the Home Builders Carbon Action Network. There's a bio-based materials collective that used to be the Northeast that's becoming a national working group, essentially, for everyone who is interested in bio-based materials. And many others. We mentioned the Hemp Building Institute. We mentioned U.S. Hemp Building Association. The Lindsay, you might drop in the chat oh my goodness, I still think of them as COSBA, Natural Building Alliance in Colorado as our sister organization. Our European sister organization mentioned in the chat, the European Straw Building Network. There's lots. So
I'll give one unsolicited kind of also touting the CASBA conference. Truly one of the most fun events I think I've ever attended from a conference. Very unconventional conference setting too. Yeah, definitely something fun. And I to say thank you all for the presentation. So insightful. And I think there's some good questions in the chat, which maybe we have a second to get to. And I think also part of that is we want to make this a longer series. So definitely more time to talk about this and a lot to chew on with things like the dynamic LCA and upcoming PCRs, stuff like that. So just like pause to say thank you so much for sharing with this group and really appreciate having you.
thanks for having us.
Thanks for having us. Yeah.
Should we stay on for questions or should we wrap it up? I
I
know.
think we can, oh, sorry.
We've I think there's a couple questions. I think real quick, we'll do one plug for our next in-person event, which is we're gonna take next month off and do our last end of year open mic night. Bro Heppold's gonna host downtown in our new offices in the US Bank Tower, so that should be swanky and nice. So keep an eye out for that. And I think are there any other CLF announcements, folks? Sandy, Rochelle?
Bay Area happy hour tonight for the CLF Bay Area.
Oh yeah.
Temescal.
Nice. Yeah, good opportunities to get together in person.
Oh, the last plug is that we're going to continue this bio-based materials conversation with the part 2 and part 3. So stay tuned for a lookout on announcements for that.
And then I think there was one question in the chat that you flagged, Sandy. I have to scroll back up about.
I think it's the question was, where do you put plumbing pipes or electrical wiring for straw build construction or the bamboo panels that don't require studs? Does it all end up exposed because you can't bury it in a wall?
No, not for straw. You can do it all sorts of ways. You can channel electrical in directly. You can put in a chase in the wall. Sometimes for plumbing, people will put it all on a framed wall just because it's easier. So have a wet wall kind of approach. But no, straw bales are really easy to channel into, and then you just plaster over them typically, depending on what your finish is.
Yeah, and from the BAMCore side, it's a two panel run that creates a hollow cavity. And so it actually is easier to install your mechanical, electrical, plumbing, et cetera, by having just an open cavity that you can then fill with blown-in insulation or what have you.
Okay, cool. Lindsay Love said she's creating a spreadsheet or tool that contrasts the various straw bale assemblies. So if you ever want to share that with us, just hit the CLF hubs up, San Francisco or LA, and we could definitely share that on our, we could definitely distribute that. Okay. Oh, somebody asked, would you be willing to make a PDF of our slides? Of your slides. Okay.
Sure.
Yeah, if you guys are willing, then just send it over to us and we'll distribute it. And then yes, and last plug, Isabella has plugged the CLF-SF happy hour in the chat. So hope you guys all go. Oh, I guess there is one other one. So for building height, what's the regulation for bio-based? I think you touched upon that, Massey, but what's the regulation for bio-based materials in USA? For
depends on your seismic zone. Typically without engineering, so prescriptive is 1 or 2 stories, but you can go higher than that with engineering.
I don't know
Yeah,
that.
the BAMCOR wall is code compliant up to 5 stories. But the codes are really different from jurisdiction to jurisdiction, so it's kind of hard to give like a single answer.
Yeah, and I'm not sure for hemp lime or hempcrete. I think one more plug, Rochelle, you mentioned Tally at the beginning of the call. We are working on Tally 2.0 right now. It is going to be out Q2 of 2025, and it's going to be free and open access, similar to EC3. So be on the lookout for that for all of you Tally users.
Awesome.
Cool.
I will be. Yeah. Okay. I think if nobody else has any other questions, maybe we leave it at that.
Great.
Thanks, guys.
Thanks, everyone.
Good to see you all.
Thanks,
Thank you.
everyone.
Bye.
Thank you. Bye.
Bye.